They're all around you right now. You can't see them, but these forces power the machines, computers, and other technology that we use every day. They're electricity and magnetism. Hey there, welcome to the channel. Electricity and magnetism are two of the fundamental forces of nature. Even though we experience their effects every day in things like electric shocks and magnetic fields, they're actually invisible. Well, that is except when they combine. When those invisible forces meet, they make light. And lots of light can make things like computer monitors, neon signs, and even lightning. These two forces were once thought to be completely separate, but scientists now know they're closely related. In fact, the word electricity actually comes from the Greek word for amber, because when you rub amber with a certain cloth, it attracts small objects like bits of paper. That mysterious force is what we call static electricity. Static electricity is caused by an imbalance of electric charges. Everything is made up of atoms, and each atom has a center called a nucleus surrounded by electrons. Electrons are negatively charged particles that whiz around the nucleus at incredible speeds. Normally, the number of positively charged protons in the nucleus matches the number of electrons surrounding it. So the charges balance each other out and the atom is neutral. But when certain materials are rubbed together, electrons can be knocked off one atom and onto another. If they stay put, the atom with more electrons becomes negatively charged and the one with fewer electrons becomes positively charged. Those separated charges make up static electricity. You might have experienced this as a shock when you walk across a carpeted room and then touch something metal. That happens because the electrons that normally prevent you from sticking to the carpet can jump to your body. Then, when you touch something metal, the extra electrons in you rush to the metal and you feel a small electric shock. Sometimes that buildup of charge can be even more dramatic. Have you ever seen a lightning storm? The ground and clouds become so electrically charged that the air between them becomes ionized. That means some electrons have been stripped from their atoms. All that free-floating charge builds until the air itself becomes a giant capacitor. Then electrons suddenly jump from the clouds to the ground, or vice versa, through a channel of ionized air. The massive flow of charge is what we see as lightning. So both static electricity and lightning are caused by electric charges. But not everything that seems electrical is really static. Take the current that powers your house. Unlike static electricity, which is a buildup of charge that stays in one place, electric current flows from one place to another. Electrons move through wires carrying energy with them. That energy can come from a variety of sources, but the most common is the flow of water. Most of us have seen how water can generate power in a hydroelectric dam. But even if you don't live near a dam, chances are your house is powered by a steam turbine. In a steam turbine, water is heated into steam, which creates pressure that spins a turbine. That spinning motion is converted into electricity by a device called a generator. No matter where your electricity comes from, though, the end result is the same. a flow of electrons through wires. Electrons can also flow through some non-conducting materials, like the human body. That's why getting an electric shock from a wire can be dangerous. If too much current passes through your body, it can interfere with the electrical signals that control your muscles and even burn your tissue. That's why it's important to protect yourself against electrical shock. Electrical circuits are designed to keep electricity flowing through them without going off track. A circuit is essentially a closed loop that allows electrons to flow from a source of energy like a battery through a wire and back again. Anytime a circuit is broken, the flow of electrons stops. That's what happens when you flip a switch or pull a plug. It's kind of like a water circuit. Just like water can't flow unless it's in a closed loop of pipes, electrons can't flow through a broken circuit. Circuits usually include a lot of other components too, like resistors, capacitors, and transistors. All of these work together to regulate the flow of electrons. But even when properly contained, electricity can be deadly. If too much current flows through a wire, it can heat up and cause a fire. That's why electrical fires are one of the leading causes of home fires. Luckily, there are several simple ways to reduce the risk of electrical fires. For example, you should never overload an outlet or use frayed or damaged cords. You should also make sure that your outlets are properly grounded. If any current leaks through your body, that path to the ground will provide a safer route for it to take than through your heart. Sometimes electricity and magnetism team up to make motors. Motors convert electrical energy into mechanical energy. In other words, they take the flow of electrons and turn it into motion. Electric motors are everywhere. They're in cell phones, cars, and even tiny robots. But all electric motors work in pretty much the same way. They use magnetic fields to turn electrical energy into mechanical energy. Here's how it works. Imagine you have a flat, rectangular piece of metal. If you place it between two magnets, it'll experience a force and start to spin. The same thing happens if you run electric current through a wire. The moving electrons make a magnetic field around the wire. If you put that wire between two magnets, the magnetic field of the wire interacts with the magnetic field of the magnets, creating a force that makes the wire spin. That spinning motion is what we harness in electric motors. Let's take a closer look at this motor from a tiny radio-controlled helicopter. First, let's look at the stator, which is basically just a fancy name for the outer part of the motor. Inside the stator are copper coils wrapped around a soft iron core. When current runs through the coils, it creates a magnetic field inside the iron. That magnetic field is then focused by the shape of the iron, making a strong magnet in the center of the stator. Now let's look at the rotor. The rotor is attached to a small battery and consists of neodymium magnets. The rotor sits inside the stator, and the magnetic fields of the stator and rotor interact with each other, causing the rotor to spin. The battery powers the rotor, but the energy ultimately comes from the interaction of the two magnetic fields. One of the most amazing things about motors is that they can create motion in very precise ways. In fact, most motors can be precisely controlled by varying the amount of current running through them. That allows engineers to create very intricate movements in everything from robotic arms to record players. But electricity and magnetism do even more than power our devices. They also help us learn about the universe. Take this particle accelerator called the Large Hadron Collider. It uses powerful magnets to accelerate and direct beams of charged particles like protons. By smashing those particles together at nearly the speed of light, scientists can study the fundamental building blocks of matter. The LHC is powered by 1,000 superconducting electromagnets. These magnets are cooled to extremely low temperatures, so they can create powerful magnetic fields without losing energy. The magnetic fields then focus the particle beams into incredibly small points, allowing scientists to study the subatomic world in unprecedented detail. Of course, we use electricity and magnetism for a lot of fun stuff. To take this Tesla coil. When high-voltage electricity is applied to the coil, it resonates at a natural frequency. This creates a high-energy current that jumps between the two terminals of the coil, producing beautiful arcs of light. And who doesn't love a good light show? We've barely scratched the surface of what electricity and magnetism can do. For example, there's a whole branch of physics called electromagnetics that studies how the two forces interact. Electromagnetics is responsible for everything from radio waves to X-rays. It's also the basis for many important technologies, including radar, GPS, and medical imaging. As we continue to explore the properties of electricity and magnetism, we'll undoubtedly find even more ways to harness their power. Maybe you'll even make one of those amazing science fair projects where the balloon pops open and a bunch of colorful liquids spill out. Who knows? Thanks for watching this episode. If you want to learn more about electricity and magnetism, check out the additional resources. And be sure to subscribe to our channel for more fun science videos.